You all know that the three important states of matter are solid, liquid, and gas. But how do we define each of these a little bit more precisely? Well, this figure does a pretty good job of it. So what we have on the left is an example of a solid, and we have some crystals in an Erlenmeyer flask. So the definition of a solid is that it is rigid, which means if you punch it, it's probably not going to move, and it does not assume the shape of its container. In other words, those crystals are going to sit at the bottom of the flask, whether it's a large flask or a small flask. And they're not going to be able to move at all in the container. So from the molecular or atomic level, which is what's depicted on the bottom, you can see that the atoms or molecules in a solid are arranged in a crystal lattice, which means that the individual atoms or molecules cannot move relative to each other. They are held together by fairly strong forces that we will examine in more detail later in this semester. One of the skills that you have to be able to master in order to be good at chemistry is to be able to correlate between what you can observe at the macroscopic level and what is actually going on with the atoms and molecules that are, of course, too small for you to see. So that's part of what I'm trying to show you in this figure. In the center, we have a liquid. So a liquid can assume the shape of a container. Okay, so for example, in this picture, you have a liquid taking up about half of an Erlenmeyer flask. If you had a flask that was thinner and taller, the liquid would go further up into the flask. It would take up the shape of the container. But it only takes up a certain volume within the container. So above the liquid, there is no liquid, and the liquid is all in the bottom half, and it has a distinct surface where the liquid ends and the gas above it begins. So molecules that are in a liquid are free to move about with respect to each other, but they're still pretty close to each other. And that is consistent with the fact that, liquids are pourable. On the right-hand side, we have a gas. So what I'd like you to look at first is the bottom part of the figure, and you can see that molecules in a gas are much, much further apart from each other relative to molecules in a liquid or a solid. So molecules in a gas, the actual structure of the gas is mostly empty space between the molecules. But then what's also important about a gas is that the gas not only can explore the entire volume of the container, but it does take up the entire volume of the container. Okay, so once you have a container, if you have a cap on it, gas molecules will move around so that they fill the entire space. Okay, so I want to start by looking at elements, and most elements are actually solid. So any metal except for mercury, mercury is depicted here, it's actually a liquid metal, are solids. And there's one other metal, gallium, that becomes a liquid just above room temperature, but technically at room temperature, it's still a solid. So the only two elements that are actually liquids at room temperature are mercury and bromine. And depicted in this flask of bromine is the dark red bromine liquid in the bottom, but you can actually see some bromine vapor above it. So there's bromine in the gas phase also has that same red-orange color. And so you can see both the liquid phase and the gas phase at the same time in this particular flask. So all of the gases are gaseous elements are nonmetals. So the ones that you need to know are hydrogen, nitrogen, oxygen, fluorine, chlorine, and then the noble gases, helium, neon, argon, krypton, and xenon. Okay, so these elements are all gases at room temperature. If you get them cold enough, they could liquefy or solidify. You may have heard of liquid nitrogen as being nitrogen gas that is cooled to a temperature of negative 196 degrees Celsius. When you get down to that temperature, it liquefies. Some people play with liquid nitrogen, freeze things in them, and some people even use it to make ice cream. And then a few of the nonmetals the rest of them are actually solids. And the most common ones would be carbon, phosphorus, sulfur, and iodine. But there are more also. Okay, so what about compounds? Well, compounds, of course, can be solids, liquids, or gases. And I just want to talk about some familiar compounds, or compounds that at least should be familiar to you. Okay, so salt, which has the chemical name sodium chloride, sugar, which has the chemical name of glucose, sodium hydroxide, sodium bicarbonate, citric acid. These are all solids at room temperature. Another molecule that you may have heard of in a biology class is called ATP. That is short for adenosine triphosphate, and that is the energy currency of living cells. Well, if you have it as a pure compound, it is actually a white solid, and we have some of it in the freezer in the biochemistry lab. And then, of course, there are many compounds that contain metals as one of their components. So, for example, copper chloride and iron oxide, also known as rust, are all solids. There are plenty of compounds that are liquids also. The one you are most familiar with is water. Now remember, water can be a gas at higher temperatures, a solid at lower temperatures, but at room temperature, it is a liquid. But several other important liquids are actually organic molecules. They're compounds that contain carbon and hydrogen and usually some number of other elements. But ethanol or ethyl alcohol, isopropanol or isopropyl alcohol, acetic acid, acetone, chloroform, ether, hexane, those are all organic compounds. I'm going to say a little more about formulas in a minute, but notice all of these have carbons in them. And then a couple of other important chemicals that are liquids at room temperature would be sulfuric acid and nitric acid. Those are both examples of what are called mineral acids. And then what about compounds that are gases at room temperature? Well, one of them that you might not have guessed as a gas is ammonia. Now, wait a minute. You might go to the grocery store and see a bottle of ammonia on the shelf. Well, that is actually not pure ammonia. What you see on the shelf in the grocery store is a solution. We'll talk more about what those are later in the semester, but a solution of ammonia gas in water. Okay, so then other gases that we've already met in previous lessons, carbon monoxide and carbon dioxide are both gases. And then we have some organic compounds, some small and simple organic compounds are also gases. So methane, ethane, propane, ethylene, formaldehyde are all in the pure form gases. Again, you may have used formaldehyde and thought it in a biology class and thought it was a liquid, but the liquid you're seeing is once again a solution of this gas in water. Some other important gases, sulfur dioxide, that's usually thought of as a pollutant. Sulfur hexafluoride. If you want to have a little fun, Google inhalation of sulfur hexafluoride and you'll find some interesting YouTube videos. And then also hydrogen chloride in the pure form is a gas. Hydrogen chloride is also more commonly referred to as hydrochloric acid, and you may have seen hydrochloric acid as a liquid, but just like the case of formaldehyde and ammonia, the liquid that you're seeing is actually a solution of gaseous hydrogen chloride in water. Okay, so you might also notice that next to the names of all of these compounds on the lists, I have included their chemical formula. Okay, so for sodium chloride, it's NaCl. For citric acid, it's C6H8O7. So chemical formulas are used all the time by chemists. You're going to have to get used to using them. And what a chemical formula tells you is simply which elements are present in the compound. Okay, so glucose contains carbon, hydrogen, and oxygen, and how many atoms of each type there are. Okay, so in a molecule of sugar, of glucose, there are 6 carbons, 12 hydrogens, and 6 oxygens, and the number of atoms of each element are indicated as subscripts in the molecular formula.